Okay, so last section. So what I can do is show the relationship between a weak acid and its conjugate base in terms of a constant that is derived from Ka and Kb. So let's take, for instance, the ammonium ion. In its reaction with water, it's going to produce its conjugate base in the hydronium ion. And then that conjugate base, the ammonia, can in turn react with water and produce the ammonium ion and the hydroxide ion. So if I look at the Ka expression for the weak acid here, which is just going to be my two products as shown here and here, divided by the reactant. Again, you eliminate the water. And then I show the Kb expression for my weak base, which is going to have the ammonium ion and the hydroxide ion, my two products, divided by the ammonia. So now if I look at those two expressions multiplied together, so if I take this whole expression here, the NH3 and the H3O over the NH4, and I multiply it by the expression for the Kb, I can see that the algebraically, the ammonium ions would cancel out, the ammonia molecules would cancel out, and so what I would have left is that the hydronium ion times the hydroxide ion is left. And what I know is that the hydronium ion times the hydroxide ion is always equal to 1 times 10 to the negative 14. So then what we can say is that if we know, for instance, the Ka of a weak acid, and we're trying to find, let's say, the Kb of its conjugate base, all we have to do is multiply those together. This would be my variable, and set it equal to Kw, which is that 1 times 10 to the negative 14. Because if I take Ka expression times Kb expression, we can see that what we end up with is just that product of H3O positive times the OH ion. And so there's a couple of other equations that you can get from this, which would be that the pKa is equal to the pKa plus the pKb is equal to Pw. And so what is that pKa? That's just taking the negative log of the Ka ion, just like the pH is equal to the negative log of the hydrogen ion. Well, then pKa is just the negative log of the Ka value. And the same thing for pKb, and then the same thing for pKw. And so that's what I've shown here. It's a negative log of Ka plus a negative log of Kb is equal to the negative log of pKw. But most importantly is that equation that we used before, that the pH plus the pOH is equal to 14. Okay, and then the very last page, we're going to talk about acid-base properties of salt solutions. And so sometimes you can put a salt solution in water. You can put a solid salt in water. One that I show below is sodium fluoride. Solid, dissolve it in water, and you end up with Na ions, aqueous, and fluoride ions. So what we know is that it's possible for this ionic substance to act like an acid or a base. So here's what we know is that some conjugate bases of weak acids, the conjugate base of a weak acid is a weak base. So for instance, I've used a generic form here, but I'll use a real molecule. So this is a weak acid. And so in equilibrium, it's going to break up into hydrogen ions and fluoride ions. So now what I know is that a fluoride ion can behave as a base. So here's what would happen. The fluoride ion of any metallic fluoride, such as NaF, as I've shown above here, can react with water and it can produce HF, right? That fluoride ion can pull one of the hydrogens out of the water and create HF and the OH ion. So here's a scenario where a weak acid can produce an ion that behaves as a weak base. So this ion, if I can get it from some other source, such as a salt, sodium fluoride, something that's not necessarily an acid, not necessarily a base, but it will behave as a base because that fluoride ion can behave as a weak base, react with water, and produce the hydroxide ion. And so we'll look at conjugate acid of a weak base can act as a weak acid. So if I take, for instance, here, ammonia weak base reacted with water, I produce a conjugate acid that itself could act like a weak acid. I could get it from some other source, say a solid salt of ammonium chloride, because that ammonium chloride could split up into the NH4 ion and the chloride ion. Now, the chloride ion won't act like anything because anions that come from strong acids will behave just as a neutral ion. And then, so what would happen here is that the ammonium ion would react with water and it would pull the extra hydrogen and form that hydronium ion in solution, increasing the power of the hydronium or the concentration of the hydronium in the solution. And then there's one other type of acids and bases that we didn't talk about. We won't get into it too much. I'm not going to push us on it. But just so you know, for future reference, there's another form of an acid called a Lewis acid. And then there's also the Lewis base. And the way they are defined is that a Lewis acid is an electron pair acceptor and a Lewis base is an electron pair donor. And then I give a couple of examples of each. And typically the best way to understand how a Lewis acid or base works, or how to qualify something as a Lewis acid or base, is to draw a Lewis diagram. All right, I think we'll stop right there.